Hello everyone, and welcome to this session about running databases on AWS. My name is Russell Nash. I'm a solutions architect with AWS, and I love databases. I love talking about databases, and I'm very much looking forward to spending the next 35 minutes with you discussing the different options for running databases on AWS. Before we get to the agenda, let's talk a little bit about the history of the relational database. The database has become such a fundamental building block of pretty much every IT architecture that we build now that we've asked it to do a lot of different workloads. So if you look at some of the different things we ask of it, we put complex queries and transactions into the database. We ask it to do rich search. We run analytics off that database. We often ask it to do hot reads. Logs we'll push in there as well. And sometimes we'll ask it to do web scale type of throughput as well. So it's no surprise that over time, the traditional relational database has started to struggle with all of these different diverse workloads. And so what's happened over time is now we've started to break out some of these workloads into very specific applications and services. So let's have a look at the Amazon services for each of these workloads. So what you can see now is we moved away from the database as a monolithic application, and we've really moved to more of a data tier. Now the bottom three of those services we're going to talk about today in some detail. So let me just cover off on the top three quickly for you here. So firstly, in the top left, you've got Amazon Elasticsearch. So Elasticsearch is obviously an open source solution, and customers love Elasticsearch for running their rich search applications. They don't love managing Elasticsearch as much, so they've asked us to manage that service for them. So that's why we released Amazon Elasticsearch. In the middle there we have Amazon Elasticache. So this is a fantastic in-memory solution for delivering hot reads. So often that will sit between your application and the database to deliver those really low latency reads that you need back to the application. And then on the top left there you have, or the top right I should say, you have Amazon S3, which is our simple storage service where it's a great place to store any kind of object. In this context, obviously we're talking about a great place to store your logs. Very cost effective and extremely scalable. So we're going to focus on those bottom three, as I said, and if you look at the workloads that are specific to those databases, we're going to look at Amazon RDS, which is great for online transaction processing type workloads. Then we're going to look at Amazon Redshift, which is dedicated for analytics. And then we're going to move to Amazon DynamoDB, which is our NoSQL service, which is fantastic for that web scale throughput that you might need. So let's start off by looking at RDS. Now when you talk to people who manage databases or use databases frequently, they often talk about three main things which keep them awake at night in terms of their database. The first is the management of that database, the workload involved in making sure that those databases are up and running all the time. The second thing is that reliability, that uptime of the database. And then the third thing I often talk about is performance, making sure that the database is performing to the level that they need it to for their applications. And so if you look at the three things that Amazon RDS provides, firstly, it's a fully managed database. So we take care of a lot of the heavy lifting for you, and we'll talk about that on the next slide. The second thing is reliability. So making sure that we give you a multiple availability zone type of approach to make sure that that database has a high availability to it. And we'll look at that as well. And then thirdly, we'll look at performance and we'll look at scalability. How do you make sure that your database performs not just for today's workload, but also as you grow into the future? On the right-hand side there, you can see the different engines that we support with RDS. And these are all flavors that you know and love, such as Oracle, SQL Server, MySQL, Postgres, MariaDB, and Amazon Aurora, which is our own MySQL compatible database as well, that's available in some of the AWS regions that we have globally. So let's talk a little bit more about the benefits of a managed database. So I've listed here just some of the things that you need to do if you're managing a relational database in your environment. And these range from the very low level at the bottom. You have to provide power and cooling, obviously, to your servers. You have to rack and stack them. You then have to install the operating system, patch the operating system, install the database, patch the database, and finally you get to the top where you're actually doing some of the more interesting work, which is around query optimization and schema optimization. Now let's look at how that stack looks on EC2. So EC2, if you're not familiar with it, is our most basic building block of virtual machine. So you can create virtual instances of Windows or Linux, and then you can install your applications on top of that. So you can see the pieces that we take care of there in yellow. So EC2 obviously takes care of the power and the cooling and the racking and the stacking all the way up to the operating system installation. And then on top of that, it's then your responsibility to then install your applications and take care of them. Let's see how RDS deals with this, and it takes it one step further. So now you can see that all of those yellow pieces now are taken care of by Amazon RDS. And this is what we mean by removing some of the heavy lifting involved in managing those databases. So all of those yellow blocks are taken care of by RDS, and that allows you to focus your attention on those top three, the most important pieces, which are query optimization and schema optimization. Let's have a look at some of the managed aspects that we're talking about in a little bit more detail. So the first is things like backup and restore. So obviously this is a vital piece of any database management system. And again, RDS takes the heavy lifting out of this for you. So we have automated backups, which will run daily backups. We take care of the transaction logs as well, which will then allow you to restore the database to a point in time. That's all automated. You don't need to worry about that. On top of that, you can also take manual snapshots as well. So if you do want to keep your own snapshots of the database, you can do that, and you can keep those snapshots indefinitely until you actually explicitly delete them. Another aspect is monitoring and alerts. So this is obviously another key piece of the puzzle when you're managing a database, is that you want to monitor that database, you want to make sure that all the metrics are within range, and you want alerts when things are not going right. So all of this comes out of the box with RDS. So all the typical metrics you'd expect, like CPU, I/O, memory, storage, etc. And then on top of that, the alarms and notifications to let you know when something's not working. So let's dig in a little bit more into some of the availability aspects of RDS. So RDS has a feature called multi-AZ, and what this allows you to do is take advantage of the different availability zones that we have within the AWS infrastructure. So an availability zone you can think of as a separate data center within a particular region. So you see here on the screen we've got two availability zones, and we have a very simple application that's not actually taking advantage of that second AZ. So what you can do with the multi-AZ feature that RDS has is allow you to take advantage of that other AZ very simply. So let's see how that works. When you set up your RDS instance, you can tell it that you want to have a multi-AZ instance. And what we'll actually do, whether you do it through the console, whether through the CLI or the API, we'll simply create that replica instance in the other AZ, and we will make sure that there is synchronous replication between the primary and the secondary. So every write that comes into that primary will not be acknowledged until it's also been written to that secondary instance. So those two are always in sync. Now what you can do is point your front-end application to read and write from the primary. So your architecture might look a little bit like this. So you can see there that those applications are both talking to the primary, and there's no issue talking across AZs because those are very low latency links that we have between the two AZs. Now, what happens if there is a failure on the primary? So let's assume that we lose connection to that primary database. RDS will now switch the secondary to be the primary. At the same time, what also happens is that the DNS entries are updated to reflect that new endpoint. The DNS change then tells the applications that you have to point to the new endpoint, like so, and processing now resumes using the new primary. Now, what happens when the original primary in AZ1 becomes back online again? It then becomes the secondary, like so. So you can see how the multi-AZ feature can really take the heavy lifting out of creating high availability. Now let's turn our attention to performance. So within RDS, there's a number of different features that we have to make sure that the performance of the database is exactly as it should be for your particular application. So the first thing that you see on the left there is the different instance class that you can choose for each instance that you have. So you can choose different size compute, memory, and networking capabilities depending on your application. And some of these instance classes range from single virtual CPUs through to machines with 40 vCPUs on them. The other thing that's very important, obviously, with any database application is the storage type. And let's delve a little bit deeper into the storage type on this next slide. So there's three different types of storage that you can choose for your RDS instance. There's magnetic, there's general purpose, and then there's provisioned IOPS. So the general purpose that you see in the middle there is great for moderate I/O type of workloads, and this is where most of our customers actually will have their applications deployed. To the left of that, with magnetic storage, this is great for smaller databases and infrequently accessed data. But if you really have a particularly high-performing application, that's where you might look to the far right there and look for provisioned IOPS. So this is where you tell us exactly how many IOs per second you want from that storage system to serve the database. Now, both the instance class and the storage type obviously allow you to do what we call vertical scaling, where you're basically making that single instance slightly bigger. Now let's discuss horizontal scaling with what we call read replicas. So here we have our application. So similar to before, we have an application talking to that primary database, and we've got a multi-AZ situation here. So we have that secondary where we're actually doing that synchronous replication. Now we can't use that secondary for any kind of read workload. It's only there for HA capability. So what we then do, if we want to spread the read workload, we actually use what we call read replicas. And these are asynchronous replicas. So we replicate asynchronously out of that primary database and then into the read replicas. And this then allows you to spread horizontally some of the read workload that you might have. Now let's talk on this next slide about consistent reads versus eventually consistent reads. So a consistent read is one where if you write a piece of information into the database, you want to be able to read it back straight away. That's a consistent read. With the read replicas, obviously, because it's an asynchronous replication, if you write something to the primary, it may not be there straight away when you read it from the read replica. But this is okay for a lot of applications. So you can see there that we've actually split the workload there into two. So our writes and our consistent reads are still directed towards the primary database, and our eventually consistent reads are then directed towards the read replicas. So a very easy way to make sure that you're getting the read throughput that you need while also managing the consistency of the database. So let's discuss a customer that uses RDS. Literacy Planet is an Australian-based organisation that has an online presence that helps children to learn how to read. Their business was growing rapidly, and they knew that they needed to add more infrastructure to cope with demand. They moved to AWS because they didn't want to increase the amount of administrative burden when they increased that infrastructure. What they find now is that they typically spend less than 5% of their time on operations, which obviously leaves 95% of the time to spend on the things that really matter to their business. Their CTO, Richard Glue, he made a comment that he said, in a physical data center, I would need at least 3 administrators to maintain the infrastructure and ensure similar levels of availability. So that talks directly to what we were talking about before with RDS managing that heavy lifting for you. So going back to our agenda, we've talked about RDS and we've talked about some of the features that it has to help manage that heavy lifting for you. Now let's have a look at a database that's dedicated to analytics, and that is Amazon Redshift. Amazon Redshift is an MPP SQL database, and MPP stands for Massively Parallel Processing. So this is a breed of database that is designed specifically for doing analytics at scale, so that you can scale out and analyze very large amounts of data. And it is a SQL database. So standard SQL that you would use in a normal relational database, you also use with Redshift. So it's very easy to get going. It's optimized for analytics, as we said before, and you can start quite small and then grow to very large volumes. So you can start in the gigabyte range and then into petabytes if you need to. It's a fully relational database as well. So you create tables as you would normally, you create relationships between those tables, and you can bring the data models that you have in your traditional relational database into Amazon Redshift as well. And again, similar to RDS, it's fully managed. So again, we take care of the infrastructure underneath, we'll back it up for you, we'll patch it, etc. So what do MPP databases look like under the hood? So here we have a typical look under the hood of an MPP database, and most of them work in a similar way, where at the top end there you have your BI clients, your SQL clients, sending SQL into the leader node, and the leader node will then take that SQL and push it out to all the compute nodes in the cluster. And the compute nodes is the layer that you scale out as you need more performance or more storage space. So typically what happens is every table that you have within the MPP system is spread evenly across every node in the cluster. So a table like that would be spread evenly, and so each node would just have its slice of the data to work with. So as that SQL query comes in, every node is running the same SQL, but just on its slice of the data. And that's how you get that incredible performance across very large amounts of data, because you're doing all that work in parallel. And that's the great thing about the MPP, massively parallel databases. There's a couple of other aspects to Redshift as well, which are extremely important in reducing the amount of I/O that you're doing in the database. The first is that it's a columnar database, and it uses columnar storage instead of row-based storage. So if you look at the table on the right-hand side there, you can see that we've got a typical table with a number of rows and columns. Now in a row-based database, the database will store that data on the disk as you would imagine that it would. This is great for OLTP type systems where you're writing and reading typically a row at a time. But when you're starting to ask analytical queries of the data, this type of storage doesn't work as well. So imagine if we're asking a question where we're saying we want the average amount grouped by state, we don't need to read the first two columns because they're redundant to our query. We're only really interested in the last two. In a row-based system, we still have to read over those first two columns. We still have to skip them even though they're redundant. If you look at the way that a columnar database stores data, because it stores it in columns, then on the disk we can simply go to the columns that we're interested in our query. So in this particular case, we're interested in the amount grouped by state. So we just go straight to those two columns and we don't read the other two redundant columns. So you just read the data that you need. And that helps to reduce I/O, speed up scans, and ultimately speed up your query performance. The second aspect of Redshift, which again talks directly to reducing I/O, is data compression. So as you load data into Redshift, we will compress it for you automatically, so that what that means is that we can get more of your data onto every disk block within Redshift. So a disk block within Redshift is 1 megabyte, and so the more of your data we can squeeze onto that 1 meg block, the more obviously we can read out every time we read a block of disk. Most customers get between 2 and 4x compression ratios, and it does vary very much depending on the type of data that you have. So a nice side benefit of this is obviously that you can fit more data into your cluster, but the main driver for this is again reduced I/O and increased query performance. The third aspect that is again about reducing I/O is the concept of zone maps. Now what zone maps do is they are an in-memory structure that looks at the blocks of data that you have on disk and will keep a track of the minimum and maximum values that you have in each block. So here we've got two example blocks, and obviously we've only got a couple of rows in here. Typically you'd have thousands or tens of thousands of values in here. But the zone map that you can see off to the right there keeps a track of the minimum and maximum dates in each block. So the idea is that when you ask a question of the data, such as give me some information where the date is a particular value, what Redshift will do is instead of reading through the blocks, which is expensive, it will look at the zone map, which is in memory, work out whether the block of data actually even contains relevant data, and if it doesn't, it will skip it. If it does contain data that's relevant to the query, then it will read it. So in this particular case, we can skip that first block because we know it doesn't contain any data that's relevant to our query, and we will read that second block. So you can imagine in a much larger system where you've got thousands and tens of thousands of blocks of data, you can actually skip large amounts of I/O by going straight to the blocks that contain the data that you're after. Now, all these three things are things that Redshift does automatically and not things that you need to necessarily manage yourself. So we've talked about reducing I/O and that leading to better query performance, but what does that really mean in terms of the response time that you might get? So here's a benchmark that one of our customers did, and they loaded up 2 billion rows into a traditional system on-premise. They loaded it into Hive, so Hive, a SQL engine sitting across Hadoop, and they also loaded it into Redshift as well. And the query that they ran was quite a simple one where they're just summarizing the data by month. And so all they were saying is just give me the summarized sales data broken out by month. So quite a simple query, but quite intense because it has to scan every single row in that database. When they ran that on their traditional system, it took just over 2 hours. It took about 35 minutes in Hive and about 12 seconds in Redshift. So you can see to what we were talking about before about trying to use best of breed engines for certain workloads. This is a great example of where you pull out a workload like analytics and you put it into a best of breed engine, and these are the types of results that you get. One of the other aspects that customers like about Redshift is the fact that you can start small and then you can grow. So the smallest database you can deploy is about 160 gigabytes, but then you can resize the database at any time to a larger one, and you can go all the way up to 2 petabytes if you need to. So what this means is you don't need to over-provision from day one. You can simply allow the cluster and the database to grow with you as you add data into it. Another aspect of Redshift which is extremely important to a lot of customers is the ability to use standard-based interfaces into Redshift so that they can use the BI tools that they're used to. So Redshift talks standard SQL and also talks standard interfaces such as JDBC and ODBC. So all the standard BI tools should plug into Redshift with no problem. So let's look now at a customer that uses Redshift in their business. So Socrati is one of India's leading advertising technology and analytics companies, and they use AWS to analyze the data that they receive and analyze that for their customers. In their move to AWS, they cut their costs by around 35%, and their CTO made a comment when he was talking about this, where he said, "We intend to grow 100x in terms of data size in the next few years." Now that's a massive amount of growth. And so what he needed was he needed a database and needed infrastructure that could grow with him even at that massive volume. And so looking at the scalability slide from before, you can see that we could easily allow that database to grow 100x without any problem. So another great example of using the managed databases that we have from AWS to facilitate growth. So we've talked about RDS for OLTP, we've talked about Redshift for analytics. Now we're going to look at DynamoDB, which is our NoSQL database, which is fantastic for web scale throughput, where you need very large numbers of reads and writes. Now the way to think about the NoSQL databases is if you look at them on an axis of scalability versus data complexity, your relational database gives you some fantastic complex data structures that you can use to great effect with very complex applications, but what you sacrifice is scalability in that regard. Where the NoSQL databases sit is up and to the left there. So they give you fantastic scalability and you sacrifice a little bit of data complexity for that. Now the reason that oval is so elongated is because there are different types of NoSQL database. So there's key value stores, which is your most simple NoSQL database, and they give you some fantastic scalability. Then you can have document NoSQL databases, and documents there we're talking about JSON type documents. And then you have graph databases as well. So graph databases are fantastic for analyzing network type of data, looking at relationships between entities, etc. Looking at Dynamo specifically, it's a NoSQL database. It started life as a key value pair, and it's now moved to more of a document database, and you can also put the Titan DB database on top of that as well if you need graph capabilities too. You get extremely low latency with Dynamo, and again it's a fully managed database. So in fact Dynamo takes that fully managed concept to a different level where in fact you don't even need to tell us how many nodes you want or how many CPUs you want. You simply tell us how many writes per second you want and how many reads per second you want, and we'll actually take care of that for you. We'll scale the infrastructure underneath for you. So when we look at low latency with DynamoDB, we're looking at two things. We're looking at how fast can we actually take a write and how fast can we perform a read, but also how consistent is that performance as well. So you can see that top line there is the number of requests that are coming in, and for most customers that can be typically very varied, but they need that latency from Dynamo to be very consistent. So that green line down the bottom there is the latency that you typically see, and you typically see it being extremely consistent. Durability is obviously very important as well, and Dynamo sits across 3 availability zones, and those writes are then replicated to between those availability zones. Again, we were talking about consistent reads before with RDS, and with Dynamo, you make the choice as to whether you want your reads to be consistent or eventually consistent. And again, all of this we manage behind the scenes for you. A customer that's using Dynamo to great effect is VAir. So this is a low-cost airline based in Taiwan. And as you can imagine, an airline reservation system is extremely important, and they use Dynamo as a critical piece of that. They need the technology to be reliable, and they need it to also cope with spikes in demand, depending on the offers that they have that are going on. The CIO, Harry Teng, the comment that he made was that he was extremely comfortable running our business critical systems in an AWS architecture. And if you look on the website, there's a great case study where you can read more about that. So in wrapping up, we've talked about 3 different types of databases, 3 different databases that have different workloads associated with them. RDS for those online transaction processing type of workloads, Redshift when you need analytics across large data sets, and DynamoDB for when you need those extremely high throughput types of environments. In terms of training, to gain more confidence and hands-on experience with AWS, you can watch our instructional videos and explore the self-paced labs. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. You can validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. And you can get more info at the URL that you see there. So thank you very much for joining us for this session where we talked about running databases on AWS. I hope you found that useful, and obviously there's much more technical detail and resources available on the website. Thank you very much.